Fair warning, to understand this explanation of how the process of finding eigenvalues and eigenvectors works, you'll need to either have some linear algebra or accept some of my statements as fact without justification. Let's start with a definition of an eigenvector. An eigenvector of a square matrix A is a non-zero vector V such that A times V equals lambda times V. Now we're going to do some algebraic manipulation with the equation AV equals lambda V. First, I'll subtract lambda V from both sides. Since AV and lambda V are vectors, we get the zero vector, not just the number 0 on the right side. Now I'd really like to factor out the V, but I can't just write A minus lambda V equals 0 because A is a matrix and lambda is a scalar, so subtracting them doesn't make any sense. Instead, I can write that V equals the identity matrix times V, using that the identity matrix times any matrix is just that same matrix again, and then rewrite the equation as AV minus lambda IV equals 0. Now when I try to factor V out, I get A minus lambda I times V equals 0, which does work because I'm subtracting two matrices of the same size now. At this point, we need some really important facts from linear algebra. By definition, V is a non-zero vector. And from linear algebra, a matrix equation BV equals 0 only has non-zero solutions if the matrix B is what's called singular. But again, from linear algebra, a matrix B is singular if and only if the determinant of B is equal to 0. So in order for V to be an eigenvector of A, the determinant of A minus lambda I must equal 0. For a 2 by 2 matrix A minus lambda I is equal to the matrix A, which we can write as A, B, C, D, minus lambda times the 2 by 2 identity matrix 1, 0, 0, 1, which can be rewritten as A, B, C, D, minus lambda 0, 0, lambda by scalar multiplication, which can then be rewritten again as A minus lambda, B minus 0, C minus 0, D minus lambda. This shows why, to find the eigenvalues lambda of A, we solve for when the determinant of A minus lambda, B, C, D minus lambda is 0. Now once we've found an eigenvalue lambda, the eigenvectors corresponding to lambda will be the non-zero solutions V to A minus lambda IV equals 0. So for 2 by 2 matrices, the solutions to A minus lambda, B, C, D minus lambda, x1, x2 equals 0, 0. Translating this matrix equation into a system of equations, we get that A minus lambda x1 plus B x2 has to equal 0, and C x1 plus D minus lambda x2 has to equal 0. In order for a linear system to have more than one solution, there has to be some redundancy in the equations. So for a system of two equations, two unknowns like we have here, one of the equations will always be a multiple of the other, which is why it doesn't matter which equation we use as long as one of the equations doesn't end up as just 0 equals 0. Further, if I'm solving a linear equation with two variables, one of the variables will always end up being a free variable, meaning I can choose any value for that variable, but that choice will determine the value of the other variable. This is why we can choose a value for either x1 or x2, and then we find the value of the other variable to find an eigenvector. So there are infinitely many eigenvectors corresponding to each eigenvalue, but since there is a specific relationship, like x1 equals negative b over a minus lambda x2, the ratio of the components of the eigenvectors is fixed. So the eigenvectors for an eigenvalue are all scalar multiples of each other.